Welcome students. I am here Dr. A.B. Nikum. We will discuss the applications of dipole moment in relation with the molecular structure. This video is for education purpose only. No copyright infringement. This copyright belongs to its rightful owner. In the applications, we consider the three applications. One, how it is useful to determine percent ionic character within the molecules. Secondly, the bond moments or group moment evaluation. And third, how it is useful to understand the geometry of the molecules. Okay, now let us consider the first application, percentage ionic character. In this application, let us consider the very simple molecule hydrogen chloride HCl, and let us assume that the chlorine is electronegative, and in formation of the bond between hydrogen and chlorine, pair of electrons is completely towards chlorine. What I mean, the hydrogen is assumed to be 100% ionic in nature. Then what is the value of dipole moment of a ionic molecule HCl? It can be evaluated by using the formula mu is equal to Q into L, where Q is charge of an electron, that is 4.8 into 10 to minus 10 electrostatic unit, and L is the bond length or separation distance between hydrogen and chlorine molecule, between hydrogen and chlorine atom in HCl molecule, that is 1.275 into 10 to minus 8 centimeter. And simple product of these two numbers leads us the value 6.11 into 10 to minus 18 ESU centimeter. It means 6.11 D by unit. But experimentally observed value of a dipole moment is 1.05 D by. It itself indicates that whatever we initially assumed, that the complete electron pair is towards chlorine and none towards hydrogen, this assumption is found to be somewhat wrong, because mu is 1.05 D by. It is much less than 6.11 D by, which is evaluated from theoretical data. Q is theoretical value, L is also theoretical value. So the percentage ionic character associated with hydrogen chloride can be evaluated by mu observed upon mu ionic into 100 gives you 1.05 upon 6.11 into 100 gives you around 17 value, and that is in percentage. So percentage ionic character is 17%. So whatever we initially assumed, that if HCl is 100% ionic in nature, then the value should be 6.11. but actual observed value is 1.05 dBi, and that's why only 17% ionic character is associated with hydrogen chloride molecule. Means the bond is not 100% ionic, but it is only 17% ionic in nature. The second application that we consider is the evaluation of bond moments. These bond moments can be evaluated by addition of the bond moments of the known bonds in the molecules or in the individual bonds. For example, these are obtained due to the differences in the electronegativity values of the two atoms in the diatomic molecules or as well as in the polyatomic molecules. HF 1.9, HCl 1.05, HBr 0.8, CH bond 0.4, C double bond O 2.3, Ci 1.2, C single bond O 0.7, Cn 0.2, all these values are in dBi units. So these literature values can be used to evaluate the bond moments of the remaining bonds in the molecules. The third application that we consider, that how the geometries or shapes of the molecules in case of organic compounds can be understood. Now let us consider that for CH4 tetrahedral molecule. This molecule is tetrahedral in nature, it is highly symmetric, and hence the dipole moment is 0. So it is non-polar molecule. Though each bond in the CH4 molecule, that is CH bond, is polar in nature, having the dipole moment 0.4 dBi, possesses highly symmetric structure or having center of symmetry, and this is the similar in case of the other molecules like benzene, naphthalene, diphenyl or PP- derivatives, which are having the center of symmetries and are planar. Hence these molecules are non-polar in nature and dipole moment is 0. So the molecules which having the dipole moment 0, either they are having center of symmetry along with the planar structure. Similarly, if we consider the molecules like CnH2n plus 1, that is alkanes, which are also having symmetric geometry and are having symmetric center of symmetry and hence non-polar in nature. Now if we replace the hydrogen from the benzene ring by any one of the other atom or radical or a group, then that particular molecule becomes asymmetric in nature and hence the molecule becomes polar. For example, in case of CH4, we replace one hydrogen by chlorine. So bond moment for CH bond is 0.4, CCl bond is 1.5 dBi, and resultant dipole moment is non-zero, and hence the molecule is polar in nature. The another example that we consider is in case of a benzene, how the value of resultant dipole moment is to be evaluated. Now, the resultant dipole moment in such molecules will be given by mu square is equal to mu1 square plus mu2 square plus 2 times mu1 mu2 cos of theta, where theta is the angle between the two groups which are present in the benzene ring. The example is given, one group is x1, another group is x2. Now theta for ortho position is 60, that for meta position is 120, and that for para position is 180 degrees. And cos of 60, cos of 120 and cos of 180 are having the values 1 half, minus 1 half and minus 1 respectively. By substituting these values for, let us consider both the groups are same, x1 is equal to x2, maybe chlorine, maybe bromine, maybe nitro group, and then the resultant dipole moment according to this formulation can be evaluated and obtained for ortho position. Mu is equal to mu1 times root of 3. For meta position, mu is equal to mu1, and for para position, mu is equal to 0. It itself indicates the dye substituted benzene derivative or molecule in which the both groups are same, identical, then resultant dipole moment is 0. While in case of ortho and meta position, it is non-zero in nature. The magnitudes of a resultant dipole moment itself indicates whether it is ortho in its position or whether it is meta in its position. Now let us consider another example that of the type AX4 type molecule, and what should be the dipole moment in these cases. The two structures that you find, one is tetrahedral, another is pyramidal. Tetrahedral structure that we know is that for CH4 or is that for MnO4 minus ion. And this is highly symmetric in nature, that we know, having center of symmetry again. But the same type of molecule, AX4, is also existing in the another geometry, and that is known as pyramidal geometry, in which A is at the apex of the pyramid and X is at the four corners and in one and the same plane, which is considered as the base of the pyramid. So in these structures, tetrahedral having mu is equal to 0 and pyramidal structure having mu is equal to non-zero in nature. So the dipole moment value itself indicates which geometry one could assign for the molecules. Now we consider the same argument towards inorganic compounds. There are different types of inorganic compounds. Let us have monoatomic molecules. All the rare earth gases or the helium, neon, argon, krypton, xenon, all these are we call as the rare gases. So all these are non-polar in nature. Why? Because center of positive charge and center of negative charge for any atoms is at one and the same place. Separation distance between the charges is 0 and hence resultant dipole moment is 0, and therefore the monoatomic molecules are non-polar in nature. Now let us consider diatomic molecules which are either polar or non-polar in nature. Homonuclear diatomic molecules are having 0 dipole moment and hence non-polar in nature because L is equal to 0, separation distance between the two similar atoms. In heteronuclear diatomic molecules, the dipole moment is non-zero and hence the molecules are non-polar in nature. The geometry associated with both types of diatomic molecules is linear itself. Let us have triatomic molecules like CO2, CS2, H2O, SO2, etc. These are the molecules of type AX2 nature. In CS2 and in CO2, you will find the linear structure. The bond angle between SCS or OCO is 180 degree, and therefore the resultant dipole moment is 0, though each bond, that is CS or CO, in carbon disulfide or carbon dioxide molecules are polar in nature, are non-zero, but the resultant dipole moment is 0, because one value is exactly opposite to that of other. Magnitudes are same, but sign is different. One is positive, another is negative. A resultant dipole moment evaluated is the summation, and that's why one cancels other here. In case of H2 and SO2 molecules, you will find the dipole moment is non-zero in nature. One is 1.85 and one is 1.6 dBi. For water, it is 1.85 dBi. Now, the another possible structure for triatomic molecules is only the bent structure. In the bent structure, you can consider that all these three atoms are in one and the same plane. Here you will find the dipole moment for OH bond is directing from hydrogen towards oxygen, from electropositive atom to electronegative atom, and resultant dipole moment is non-zero here. The another molecule we consider AX3 type, tetraatomic molecules. Again, here are three possible structures. One is trigonal planar, means 3x and 1a all are in one and the same plane. Trigonal planar. Angle between XAX is 120 degrees. In case of T-shaped structure, angle between XAX is 90 degree. And in case of trigonal pyramidal structure, you will find 3x are in one plane and one, that is dissimilar atom, that is A here, is at the apex of the pyramid. So the dipole moment values of these three, if you try to evaluate, then you will find those are different. Those are different. And according to the magnitudes, which magnitude it has, it is very, very smaller or it is very, very higher. It indicates which structure one could assign for these molecules. Now one can give the different structures here, that of suppose BF3 molecule, CF3 molecule or NH3 molecule. So all these three are the examples of these three types of structures that one could find. And the another application that we find here, that the dipole moment value also useful to understand whether the molecule having cis or trans structures, whether the molecule is cis isomer or trans isomer. The good example one can consider here is that of fumaric acid and malic acid. Molecular structures are same, but the structural formulas or arrangement of the atoms or groups in the molecules is different. And you will find here, in case of trans structure, the COOH and COOH groups are completely opposite. And this molecule, trans molecule, that is fumaric acid trans molecule, having center of symmetry with respect to carbon-carbon double bond. if we consider the center of symmetry is at the center of carbon-carbon double bond, then if we move from one COOH group through center of gravity to the other side, you will find the same group which is present at the same distance from the center of gravity itself. And that's why the molecule is trans in nature. So the trans isomer having center of symmetry and it has the zero dipole moment. And while the cis isomer for malic acid here, the COOH and COOH groups are towards one and the same side. So there is no center of gravity. There is no center of symmetry for that particular molecule, and hence it has non-zero value of dipole moment. So the isomers, whether it is cis or trans, can be easily identified from the dipole moment values itself. So how this particular simple physical property dipole moment is useful to understand the structures or geometry of the simple molecules. Now let us stop here. Thank you for your patience. We continue the same topic, that is of investigation of molecular structure, in our next lecture. Thank you.